In my last video, I explained what is A divides B or B is divisible by A, and what are the properties for the integers A, B, C. A divides 0, 1 divides A divides A, like that. Those properties we have learnt. Now we'll continue with that. If A and B are the integers, then an integer D is said to be a common divisor of A and B if D divides A and D divides B. A and B are the integers. D is said to be a common divisor of A and B if it divides both A and B. Because 1 is a divisor of every integer, okay, and I can say 1 is a common divisor of A and B. I know this. 1 is a divisor of every integer. So I can say 1 divides A, 1 divides B. Therefore, I can say 1 is a common divisor of A and B. So I can say a set of common divisor is non-empty. For any two integers, set of common divisors is non-empty. But the thing is, suppose these two integers are equal to 0, then what happens? We know every integer divides 0. We know every integer divides 0. This we know, right? So I can say, suppose if both A and B are equal to 0, then every integer is a common divisor of A and B. In this case, they are integers. There is no condition for A and B. They can be any integer. So 1 divides every integer. So I can say 1 divides A and 1 divides B. Therefore, set of common divisors for A and B is non-empty. Now the thing is, I have got A equal to 0 and B equal to 0. Then every integer is a common divisor of A and B. For in this case, every integer is a common divisor of A and B when A and B are equal to 0. Therefore, I can say set of common divisors for this is infinite. Okay. Here there was no condition. In this case, I am taking A equal to B equal to 0. So in this case, set of common divisor is infinite. Now suppose the situation is different. Any one is 0 among A and B. Say suppose A is 0 and B is non-zero. Okay. Then there are only finite number of common divisors, and among those finite number of common divisors, the largest one will be the GCD, greatest common divisor of A and B. Okay, I repeat, if you have integers A and B, then D is said to be a common divisor if D divides both A and B. Since 1 is the divisor of every integer, for any integers A and B, set of common divisor is non-empty. If both the integers are zeros, then set of common divisors are infinite. If any one among the integers is equal to 0, then set of common divisors are finite. So among the finite set of common divisors, the largest one will be the GCD, the greatest common divisor. So let us define GCD. Let a and b be given integer, at least one of them is different from 0. Then the greatest common divisor of a and b, which is denoted by GCD of a and b, is the positive integer which satisfies these two conditions. We can say d as a common divisor, greatest common divisor of a and b, if d divides a and d divides b. And if there is any other integer which divides both a and b, then that integer must be less than or equal to d. That must be less than or equal to d, then only I can say that d is the GCD of a and b. Okay. Now let us prove one important property. That is, given in integers a and b, which are not both of them are 0. Okay. Then there exists an integer x and y such a way that GCD of a and b, that can be written as linear combination of a and b, that is ax plus by. Now see, I'll consider a set of all linear combination of a and b. Say let us consider a set S, which is a set of all positive linear combination of a and b. I'll write the set like this, say AU plus BV, such that I'm taking the positive linear combination, okay, where U and V are the integers. You can observe that this is set of all positive linear combination. So this set is non-empty. Okay, this is non-empty. Now for example, if A is non-zero, okay, if A is non-zero, then mod A is my integer, then this I can write it as linear combination AU plus B into 0. Now this element belongs to my set S, okay. This integer, any integer, this can be written like this. If this is not equal to 0, then this can be written as a linear combination. Therefore this element belongs to S. Now I can choose U to be 1 or minus 1 according to that whether A is positive or not. Okay. So, right, we choose U equal to 1 or minus 1 according to whether A is positive or negative. Right. Now, by well-ordering principle, this set must contain a smallest element, right? So, let me call this as D. By well-ordering principle, S must contain a smallest element say D. Thus, there exists an integer. When this D belongs to S, then there exists some integer, say x and y, such that this D can be written in terms of linear combination of this, right? So let me write D as ax plus by. Sorry, got over again. So the thing is, if D belongs to set S, then for some integers x and y, I can write D as ax plus by. Now I claim that this is nothing but the GCD of A and B. Claim that This D is nothing but GCD of A and B. Now let us see how it is. By division algorithm, we can obtain the integers say Q and R such a way that A is nothing but say QD plus R, where R is greater than or equal to 0 and it must be less than D. This way of writing we know. Now I can rewrite R as A minus QD. Okay, what is D? D is nothing but AX plus BY. Write it like this. I'll rearrange this. I'll take out A common in this so that this will be A into 1 minus QX plus B into say minus QY. Okay. Now see, this is again in the form A into some linear combination plus B into some linear combination of integers. Okay. So this R belongs to set S now. Before that, see, if this R is positive, suppose R is positive, then this representation gives me that R belongs to S. If R is positive, then from this representation, I can say that R belongs to S. If it belongs to S, then see, here I know R is less than D. It is positive and less than D. If I say R belongs to S, then which contradicts the fact that D is the smallest element in my set S. By well ordering principle, I have considered D as the smallest element in my set S. When I represent it like this, here I am getting R being positive, which belongs to set S. Therefore, it contradicts the fact that D is the smallest element. Okay. Therefore, I cannot consider R being R greater than 0. So, should say R is equal to 0. When R becomes 0, A equal to QD. A equal to QD. This implies D divides A. Okay. Same argument I can use to prove D divides B. Okay. So I've got D divides A and D divides B. This is not enough to say that D is the GCD of A and B. I have to check for another common divisor if there exists. Then that must be less than or equal to D. I have to prove that part, second part. Now suppose C is any arbitrary positive common divisor of A and B. Okay. If C is an arbitrary common divisor of A and B, then I can write C divides AX plus BY for some integers X and Y. So I can say C divides D. When this is the case, then this we know, right? So I can write it like this. C must be less than or equal to D. So that D is the greatest common, greater than every positive common divisor of A and B. Therefore, I can say D is nothing but the GCD of A and B. We have proved D is nothing but, D divides A and B. We have proved that. Then if there exists any positive common divisor of A and B, say C, then that is less than or equal to D. In this case it must be equal to D. Okay, therefore D is GCD of A and B. See, I can suppose I have for example, suppose I have A equal to 6 and say B equal to 15. Okay, now what is set AS? It's a set of all linear combination of AU plus BV. So I can write it as say 6 into minus 2 plus 15 into 1 and 6 into minus 1 plus 15 into 0, like that I can write the set yes. So this is nothing but actually 3, 9, 6, like that you'll get. Now among all this, 3 is the smallest element in my set. D equal to 3. It is the smallest element in the set. You can observe that this is nothing but the greatest common divisor of A and B, that is 6 and 50. Now let us look at one more definition, that is relatively prime. So we know we can say D as the greatest common divisor of two integers, say A and B, not both of them are 0. If D divides A, D divides B, and for some other, for any arbitrary common divisor C, then that must be less than or equal to D, then we can say it as a greatest common divisor. Now the thing is, what happens if that greatest common divisor value is equal to 1? That means D is equal to 1. Then we say those two integers are relatively prime. Okay, two integers A and B, not both of which are 0, are said to be relatively prime whenever their GCD is equal to 1. So when the integers A and B are relatively prime, I can say D equal to AX plus BY, and that D value is equal to 1. Therefore, I can say 1 equal to AX plus BY for some integers X and Y. And the other way is also true. The same thing we are going to prove now. A and B are the integers and not both of them are 0. Then these two integers are relatively prime if and only if there exists some integers A, X and Y in such a way that 1 equal to AX plus BY. We'll prove this. Let us take the first part. If A and B are relatively prime, okay, B are relatively prime, then I can say that GCD is equal to 1. This is by definition. Then from the theorem which we have proved earlier, there exists some integers X and Y in such a way that I can write the GCD as AX plus BY, right? I can write for some integers X and Y, one is nothing but AX plus BY. The second part is, first part is over. Now the second part is, I have to show if 1 equal to AX plus BY, then A and B are relatively prime. So suppose converse part. suppose 1 equal to ax plus by for some choice of x and y, then D is a GCD of A and B, then it implies D divides A and D divides B, then D also divides ax plus by for the integers x and y. Then what is ax plus by, which is equal to 1, right? So thus D must be less than or equal to 1. Since we know that D is a positive integer, D must be equal to 1. Therefore, I can say GCD of A and B is equal to 1. I hope this step is clear. This we have proved actually. If A, B, C are the integers, then A divides B with B not equal to 0. Say A divides B with B not equal to 0. Then modulus of A is less than or equal to modulus of B. The same step I have used here. Since D is a positive integer, D must be equal to 1. Therefore, GCD of A and B is 1, which is nothing but A and B are relatively prime. Now, suppose I have, say, GCD of A and B as D. Okay, then what happens to GCD of A by D and B by D? What is this? We can observe that these A by D and B by D, they look like fractions, right? But they are the integers, and we also know D divides A and D divides B. So it's possible to write for some choice of x and y, D can be written as ax plus by. Now so if I divide by D, then I'm getting 1 equal to A by D into x plus B by D into y. A by D, I'll rewrite it as A dash and B by D as B dash. Now you observe that for these two integers, there is a GCD. I'll take it as C. Okay, C is the GCD of A dash and B dash. Then C must divide A dash x plus B dash y for some choice of x and y. What is this? A dash x plus B dash y is 1. So C divides 1, that means C is 1. That means the GCD is 1. It means GCD of A by D and B by D is equal to 1. So it's a corollary to the previous theorem. If GCD of A and B is D, then GCD of A by D and B by D is equal to 1. You can observe with an example. Suppose I have two numbers minus 12 and 30. Their GCD is 6. So when I divide these two integers by the GCD, I'm getting minus 2, 5. You can observe that its GCD is 1. Now let us look at the second corollary. If A and B are relatively prime and A divides C and B divides C, then AB must divide C. See, if A divides C, then I can write C as product of A into R for some integer R. Okay. Similarly, I can write B divides C as, say, C is equal to B into S for some. Since GCD of A and B is equal to 1, for some choice of x and y, ax plus by equal to 1. Now I'll multiply this whole equation by C so that it will be CAX plus CBY equal to C. This is same as writing C into AX plus BS. This C I'm replacing it by this, plus BY into this C I'm replacing it by this AR. Okay. Now this can be written as AB is common. So XS plus YR. This means C is equal to AB into some linear combination of integers. What does it imply? It implies AB divides C. Hence the proof.